Hi everyone, welcome. My name is Ibrahim Ruiz Carrillo. I'm from the Universidad Autónoma de Zacatecas and I'm going to present my work called Co-addition effect in the martensitic transformation of nickel, manganese, titanium, iron, boron alloys. In this presentation, I'll go over what shape memory alloys are, also what martensitic transformation means, and then I'll show you how replacing some nickel with copper in a nickel manganese titanium alloy modified with iron and boron affects the transformation temperature, the transformation enthalpy or latent heat, and the thermal hysteresis. So first, shape memory alloys are metals that can be strained beyond their apparent elastic limit and recover their original crystalline structure. These alloys do this thanks to a phase transformation in which atoms rearrange before experiencing permanent plastic deformation. This transformation can be reversed either by removing the stimulus causing the strain, such as mechanical stress for example, or by heating. The nickel manganese titanium system is one of the most studied shape memory alloy systems today. So for example here, we have the difference between a deformation that cannot be recovered and one that can be recovered. This happen in a shape memory alloy. But for example, in a common alloy, such as steel, this doesn't happen. Only this. If you strain it, you can't recover its original structure. Now, the name of this phase change is martensitic transformation, and it's defined as a solid state transformation, diffusionless, where atoms keep their neighbors at the same distance but change the way they are arranged. It happens between a high symmetry phase, stable at high temperature, known as austenite, and a low symmetry phase, stable at low temperature, known as martensite, and it can occur either by changing the temperature or at constant temperature, but by applying some stimulus, maybe stress, as we already saw. In our work, we used differential scanning calorimetry, or DSC, to study the transformation as a function of temperature. As you can see in figure 2, there are four important points, AF and AS, that indicate the temperature at which transformation to austenite finish and begin respectively, and similar MF and MS for transformation to martensite. But in a certain range of temperature, both phases exist at the same time. So to get a single transformation temperature value, we use the average of MS and AF. This is a representation of DSC thermogram and indicates where we can locate MS and AF to be able to apply the average. This value is known as martensitic transformation temperature, or MT. So for methodology, we first weight each element, changing the amount of copper to replace some nickel, otherwise keeping the total mass at 4 grams. Then we melted the samples in an electrical furnace to make ingots. Later, they were encapsulated in a quartz ampoules and heat treated at the 1273 Kelvin for 48 hours. After that, we cut a small piece of 20 or 30 milligrams using a wire electrical discharge machine and cutting pliers. And finally, ran DSC scans from 403 Kelvin down to 203 Kelvin at 10 Kelvin per minute. This was the heating rate. So here in the thermogram, we can see that adding 1% of iron shifts the transformation to higher temperature compared to the ternary alloy, from here to here. And adding copper shifts it back down, from here to here, 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 and finally here. Table 2 shows the transformation temperature that, as we already saw, this is the average of MS and AF. The transformation enthalpy, that this is the average of integration of exothermic and endothermic peaks for each sample, and thermal hysteresis, that this is the difference between this value and this value for each sample. We obtain these values for all alloys except copper 2 because these had irregular peaks. For example, here and here, the peak never finish, so these data are not reliable. Now, in figure 5, it's shown how these three variables change with variations in chemical composition. The transformation enthalpy trend is very similar to the transformation temperature. It rises with iron addition and then drops again with copper addition. And for the hysteresis, there's no clear trend. So our conclusions were: as can be seen, iron addition increases the martensitic transformation temperature and transformation enthalpy of a ternary alloy, while copper addition decreases them. For hysteresis, no clear trend was found, and two of these alloys showed a martensitic transformation around 273 Kelvin. And that's it. Thank you for your attention.